SQL database is always encrypted?
Hi, I'm Nicholas Ogg, one of the engineers on the Always Encrypted team in Microsoft. In this talk, I will be presenting our work on Always Encrypted, a feature in Microsoft SQL Server. As a brief agenda, I will be discussing the motivation for Always Encrypted, followed by an overview of the feature and some of the challenges we faced building it. Finally, I will end with a brief discussion on the related work in the area. As more and more workloads move to the cloud, additional security risks are introduced. Whereas previously users knew who all had access to the physical machines hosting the data, this is no longer the case in the cloud world. Cloud service users no longer have control over system administrators who might have access to the machines that host and process the data. Because of this, there is a need to protect confidential information from high-privileged users such as database and system administrators. We present Always Encrypted, the Microsoft SQL Server feature providing cryptographic data protection guarantee. Always Encrypted expands on existing encryption at rest and encryption in transit mechanisms to also provide encryption and use protections. The protections Always Encrypted provides goes beyond classical access control mechanisms, which do not prevent system administrator level attacks. As an example, in normal access control environments, a DBA generally can read all data in the database, and system administrators could attach a debugger to the running process and read values out of memory. Finally, Always Encrypted provides these protections while still allowing for limited computation over the encrypted columns. Let's now go into how Always Encrypted makes these guarantees. Always Encrypted introduces client-side encryption to SQL Server. To do this, we leverage the SQL driver managing communication between the customer's application and the database. The user specifies a column in the database to be encrypted. From that point on, any insert or update queries will transparently encrypt the column values on the client machine via the driver. The encrypted values are then transmitted to the database. Similarly, on read queries, the driver will transparently decrypt the encrypted values coming from the database before returning the results to the application. This guarantees that the database never sees unencrypted values while still allowing clients to operate over plain text data. Importantly, the database does not see the encryption keys used for the data. We use a two-tiered encryption scheme. The data is encrypted using a key called a column encryption key, or CEK. This in turn is encrypted by the column master key, or CMK. The encrypted CEK is stored in the database while the customer has full control over the column master key. Without access to the CMK, an administrator will have no way of reading the encrypted data. We support multiple encryption types. Deterministic encryption, where the same plaintext value maps to the same encrypted value. Randomized encryption, where the same plaintext values map to different encrypted values. And finally, a variation of this with a bit set indicating support for enclave computations. We will look more into this in a few slides. The different encryption schemes provide different levels of guarantees and computations over the columns. Normal randomized encryption provides the most security guarantees while allowing for no scalar operations over the data. Due to the same plaintext value encrypting to the same encrypted value, deterministic encryption opens up the door for performing equality queries. This is done simply by comparing the two encrypted values. Randomized encryption with enclave support opens up more operations, allowing us to support range and light queries as well as indexes. We cover the information leakage of each encryption scheme in the paper. We will now discuss how enclaves let us support additional queries over the encrypted values. As a bit of background, an enclave allows users to run code in a protected environment. The enclave acts as a black box, preventing even the operating system and kernel from reading the memory within it. This gives us an execution environment for performing comparisons on the encrypted columns. To perform a simple less than or greater than comparison, the client sends the column encryption key to the enclave via a secure channel. For details on how the key is sent, as well as the additional processes required to establish trust in the enclave, see Section 3 of our paper. Once the column encryption key lands in the enclave, SQL Server can send comparison requests to the enclave. The enclave then decrypts these incoming values and performs the comparison on the plaintext versions. It then returns only the result of the comparison back to the database engine. Importantly, the plaintext values and encryption keys never leave the protected enclave memory. To provide compatibility with normal SQL Server operations, as well as reducing the implementation complexity, we run a subset of SQL Server called expression services in the enclave. This component is typically used by SQL Server to run scalar operations on data, so plugging into this allows us to run operations without extensive code changes. Exposing comparisons on encrypted data using the enclave opens up a lot of interesting possibilities. We can relatively easily support equality, range, and like queries. We also support indexing on the encrypted columns by storing the encrypted values in their plaintext ordering. For lookups, we traverse the underlying B tree, performing each comparison in the enclave. Let's look at indexing in a bit more detail. On the left, we see the B tree of the index in SQL Server. While the values are shown in plaintext form, in reality these are encrypted in the database. On the right, we will show the comparisons performed in the enclave. As we traverse the index trying to place the value 7 into it, we perform all of these comparisons within the enclave. In this example, we would first compare the encrypted value of 7 with that of 4. These values are sent to the enclave, which decrypts them and then performs the comparison on the plaintext version. The enclave returns only the result of the comparison back to SQL Server. We continue performing the comparisons in the enclave as we traverse the index to find the correct spot in the leaf page. Unfortunately, there are many details we cannot cover in today's talk. However, there were many interesting challenges we had to solve in order to ship Always Encrypted. Let's briefly look at a few of the major challenges. We cover these in much more detail in the paper. First, before the client sends the encryption keys to the enclave, we must make sure that we are indeed talking to an enclave and that it has not been tampered with. Attestation is the process we use to verify these requirements. Next, there were challenges specific to index recovery. During index recovery, SQL Server must occasionally traverse the indexes. As mentioned before, this requires the comparisons to be performed inside the enclave with access to the column encryption key. However, during recovery, no client has sent the keys yet, so we cannot perform this comparison. We came up with a solution allowing us to defer these comparisons until after a client has sent the keys, effectively postponing recovery of that index. Finally, we worked hard to improve the performance of Always Encrypted. Using the standard TPCC benchmark, we encrypted several of the PII columns, such as the customer first and last names. After our performance work, the enclave was no longer the bottleneck during the benchmark. Details on the various improvements are given in section 4.6 of our paper, with the benchmark results given in section 5. Always Encrypted builds on a large foundation of research on computations over encrypted data. Other methods for performing computations exist, such as homomorphic encryption, property-preserving encryption, and garbled circuits. However, these methods often suffer from large performance impacts, making them infeasible for use in production scenarios. There has been research into using trusted execution environments such as enclaves as well. Notably among these are systems such as TrustedDB and Cypherbase. Always Encrypted expands on this rich work, showing that enclaves can be used to provide computation over encrypted values in an industrial database product. In conclusion, we have covered the motivation behind Always Encrypted, followed by an overview of the feature and some of the challenges we solved in order to ship. If you have further questions, we cover the feature in our public documentation. Additionally, feel free to email any questions you might have to sqlalwaysencrypted@microsoft.com. Thank you.
Thank you, Nicholas. Are there any questions? I don't see any questions yet on the QA panel. How are you? So right now, could you summarize which, so whether you have any ideas about supporting aggregation on encrypted data?
So aggregates present a bit of a challenge in terms of like security, especially like math or sums, especially as well as division. If you go there, present fun challenges because you can essentially reverse engineer the plain text data if you have unlimited access to, especially summation and division. So those are harder to support. Other aggregates such as order by or group by statements are easier to support. Yeah, and for like summations and stuff, it requires a slightly different architecture to verify that the summation is indeed coming from the end user and not just a malicious database.
Mm-hmm. Thank you, Nicolas. So we have a question from Hamid Pirahesh. Please commenting whether you could comment the strength of order preserving encryption and compare with your method of decrypting in enclave.
Raghav, do you want to take this one?
Sure, yeah. So order preserving encryption, as proposed in previous literature at least, leaks a lot more information in addition to the order. Whereas, you know, our technology is based on using enclaves, and that leaks exactly the order. It doesn't leak any more information. So in that sense, we are more secure than most competitors. There was one work by CryptDB on doing this so-called mutable encryption schemes, where on every update, you'll go and re-encrypt some of the other records. So we don't have that, and that poses a lot of problems with concurrency control and so on. So we don't have that problem either. So in the sense, we have the best of all the worlds in that sense in terms of order preserving. We leak exactly order, nothing else, and we don't have this mutability property. So we are kind of a standard encryption scheme.
Thank you, Raghav. And we have a question from Alex Schreier, whether you can talk about SGX and whether its current limitation performance are sufficient to support what you require from enclaves, or what is still missing?
So in terms of SGX, it has a couple limitations, such as it has a pretty small amount of memory available to the enclaves. I believe it's about 128 megabytes or so total across all enclaves running on the machine. So especially in a cloud world where you'd ideally run multiple enclaves, that severely cuts down how much memory you can use. But our design of running only the expression services component inside of the enclave doesn't end up using that much memory. So we're able to work within those bounds. One of the other limitations right now is that current Intel server SKUs with SGX on them only top out at about 8 cores or so. So the workloads only can run on fairly small databases in terms of like number of cores.
I just want to add that multi-socket SGX is coming out in a year. So, you know, it's a year or so. So this is a very short-term limitation.
Yeah.
Okay, so with multi-socket, you expect you can take a better advantage of SGX.
Yeah, I mean, both CPU, even memory, the enclave memory would increase to multi-gigabytes, right? Although we don't need it, like Nicholas just said, but many of the limitations are really short-term limitations for now.
Great, thank you both. Any other questions? Okay, so I have one more question from Shell Finkelstein. So this is about deterministic is faster than randomized, but it leaks the distribution, which is significant if the distribution values is known, if the expected distribution values is known. Like, this is more about what advice would you give to the customer about when the comparison of deterministic and randomized.
So if you don't need any operations on the data, randomized encryption will like mask the distribution of the data because like all the values map to different things. If you still need operations, randomized encryption with enclaves is better because you can perform operations on it. And in terms of data leakage, if you aren't building indexes over it, like you have better protections against like ordering or the distribution leakage.
So is there a way for the customers to estimate the performance overhead?
So in terms of like the performance, we do cover it in the paper. We compare plain text versus deterministic versus randomized encryption with enclave. So all three of them we cover.
And one question from Jin Zhang, how do you deal with key rotation?
Yeah, so that's a good question. As I mentioned, we have a two-tiered encryption scheme where we have a master key and then a column encryption key. So often rotating the master key is enough, and that doesn't have to deal with like a full table or a full data re-encryption. You can rotate the column encryption key, however, which does essentially rotate everything. Always encrypted with deterministic encryption and randomized without enclaves. We provide tools to do that. It'll download all of the data to the client, perform the rotation there, and then upload that back to the server. With enclaves, we also allow you to perform the key rotation within the enclave, which significantly saves on time because you don't need to transfer the entire data.
Yeah. In fact, we do it as an auto table, auto column query, right? So it's a DDL operation for us.
Yeah. Great. So if we are ready to, we can have a live QA question about, I think we can switch to a live QA session. Thank you, Nicholas and Raghav, for your presentation. I think this was the last presentation of the session. So I think we are ready to do a general QA session unless there are no more questions. So I think all panelists, all presenters can answer to questions that come up. We can maybe give a few minutes to everyone to. I think we can thank you everyone then. We can continue the questions on the Slack or we can have on the QA section. I'd like to thank everyone for presenting. I'm sorry if I'm pronounce someone's name. That's highly likely. Thank you very much.
Thank you, Eva, for doing a great job.
Thank you.
Thanks. Yeah, from me also, Eva. Thank you. I just typed it.
Have you done session sharing before? Eva? Oh,
Oh yeah, that was my first time. Yeah.
Oh, it was your first time?
My first virtual, I think. Yeah, I think that's my first time.
You mean I was asking about even non-virtual?
Or including non-virtual, yeah.
Oh, wow.
I was trying to remember, yeah.
You are the second one. Mila did it for the first time yesterday. I didn't even know until the very end that was her first one. Wonderful. Great job. Thank you.
Thank you. That presentation is also...
Bye. So there's some social thing. I'm curious to see what's there. There are 3 or 4 of them apparently.
This is a challenge for Mohan, right? There's a social event and he can only go to one of them, not all 4.
Hey, you can switch, right? You can do hang around here for a bit and then there for a bit and so on. Sure. I actually don't know what these are. Let me see. Zoom side chat. Oh, wait, that was yesterday. Wednesday. 3 to 4. Women in DB. Hey, are you ladies not going to be there?
Yeah, I think I will join shortly.
Oh, okay. But it requires some...
Mohan, I think everyone is invited. You can go too.
I thought no. I thought they had limits and you had to register and so on, right?
I registered, but I'm not sure there are limits. I haven't.
Oh, I thought the whole point of that registration was they didn't want way too many people showing up there. At least that's what I recall seeing, a few days ago, some message floating around. Okay, let me go. Okay, that's one. What are the others though? Let me see.
All right, guys. See you later.
Okay, bye-bye.
Bye-bye.
Transitioning research to practice. The NSF Convergence Accelerator. Zoom side chat with Tamar Ozu. And Zoom side chat with Raymond, Hong Kong University of Science and Technology. Okay, a couple of them are starting later, but 2 I think have already started. Okay, bye-bye.
Bye, everyone.